Okay, so this will be a much more sort of modest in scope sort of presentation than the keynote, but it is, as I was thinking about it earlier this morning, it is sort of an elaboration really of one of the points that came up in Dr. Gosling's talk, and this is about the relationship between the real-time elements in flight software and what I think are legitimately non-real-time elements in flight software that maybe we don't think about in as comprehensive and productive a fashion as we might. So the idea is something like this. Flight software, I think when we're designing spacecraft flight software, we think of it as being a real-time system. We all know that you have to have that real-time system to drive the hardware, to respond to interrupts. It's a robotic vehicle that has to respond in deterministic time to stimulus. And that's been the case since the first the first computers were being used on spacecraft. But as the computing capability on spacecraft has grown, I would argue that the systems that the missions become more capable, and a second system area, second domain of flight software emerges, a non-real-time system that manages data and doesn't have to play by the same rules as the real-time system that drives the spacecraft. So what I think this system is a background system. That is the real-time flight software that operates the robot. It has to have priority, obviously, or else you lose the spacecraft. In the background, though, is the system that is qualitatively different in nature from the flight software we were used to thinking about. It's non-real-time. It's discretionary rather than safety-critical. It's time-sharing rather than interrupt-driven. And there's a space for it on the flight processor, even if you don't have a separate processor for it. When we look at the scheduling theory for real-time systems, the sum of the allocations of time for real-time tasks theoretically is not supposed to add up to more than about 60% of the CPU time, because you have to have the remaining 40% as margin to make sure that you never miss deadlines. Well, that other 40% we think of as being idle time on the processor. And it can be idle time, but it doesn't have to be. You can be doing things during the idle time. And that idle time is what's available for this second system, the interruptible tasks, the data management tasks, everything that's not really real time. The nature of this second system in flight software, I would contend, is something like this. All the tasks run at the same priority. It's like a desktop as opposed to a real-time system. Everything runs at, the priority is not important. What's important is time sharing, time slicing. You might have a number of these background subsystems, and to the real-time flight software, they all look like idle because they're all interruptible at any time, just like the idle tasks. The tasks don't have deadlines. It's fine if they lock each other out for actually fairly prolonged periods, as long as everybody gets a chance to run at some point. Every task releases CPU time when it finishes its work. And so typically they'll be blocking on some sort of, they'll be waiting on something and waiting for an opportunity to run and taking turns running in the background rather than responding to stimuli by interrupts by handling the signals, for example. So as a practical example, as a case study, the case that I'm most familiar with, we can think of, for example, the flight software on the Curiosity rover is a terrific example of the real-time system that drives the robot. Other good approaches are possible, but that's a good example of of what a good real-time robotic system would look like. I will propose here, just for the sake of argument, that an example of the second system that I'm talking about would be something like the interplanetary overlay network architecture implementation of delay-tolerant networking that JPL has been advancing over the last few years as an approach to the design of a flight software non-real-time system, a background second system. And again, other good approaches are certainly possible, but I'll talk about that one a little bit. So here's an overview of the design of that ION system. It's actually pretty simple. There are multiple tasks that run concurrently. They all run at the same priority, at the idle priority of the system. There can be multiple application tasks. There can be multiple routing tasks, transmitting tasks, receiving tasks, all running as daemons. And they all interoperate by reading from and writing into an object database. Here's an overview of the general design principles of the ION system. It uses shared memory. It's perfectly straightforward about using shared memory. There may not be any protected memory, so shared memory is what you've got. But this actually can be an advantage rather than a disadvantage, because shared memory is a really efficient way to pass data between tasks. It heavily uses zero-copy procedures. It leverages shared memory to minimize the overhead of processing, of copying. And so it'll encapsulate data in layers of overhead that are abstract and are separate from the data itself, rather than copying and embedding. So the same data object can be shared by multiple tasks. There's reference counting, and that prevents deletion of data that is being used by other tasks. And a less obvious point is the software is designed for a lot of portability. Because this is not necessarily a familiar programming model for people who are developing flight software, we need to make it easy to develop in an environment with good programming support, such as Linux, and so that you can then recompile it, run it on VxWorks, for example, or RTEMS, without having to worry about having to change anything. It works the same way. So portability is important. And so in that sense, and here's the conceit of the presentation, this background system, the second system of the flight software, is similar in many ways to the real-time flight software, but in some ways it's the exact inverse of what we do in flight software in real-time systems. And the key here is that the two systems can coexist in perfect harmony. We've demonstrated this. I'll have an example toward the end. There's no incompatibility between real-time flight software and background systems that do data management in a completely non-real-time way, operating within the same processor. What the foreground and background real-time and non-real-time systems have in common is most of the cultural values of flight projects. You can't develop the background software in a casual and sloppy way. You can't jeopardize the project schedule. You have to minimize the coupling between the modules. You still can't do dynamic memory allocation, because you can't risk using both the system memory so that you lock out real-time tasks. You have to be efficient. You have to make the best possible use of available resources. You contain faults. You tolerate them if possible. You test as you fly as you test. You have a formal and controlled development process. But there are significant areas where they differ, I would argue, profoundly, where they're exactly inverse. And the kinds of things that I'm thinking of here are, first of all, what it is that you optimize. In particular, determinism and portability. what do you do about mutual exclusion? What do you do about data sharing, message passing, and memory management? So starting with what you optimize. In the foreground real-time system, reliability is absolutely paramount. If you don't have reliable real-time software, you lose the spacecraft. And so you have a fixed scope. You fix it early in the development of the system. And because it's fixed and constrained, and it has to be in order to be deterministic, you can have you can afford to have mission-specific design, comprehensive testing. That's where your reliability comes from. For the background system, the reliability is important, but what's really more important is efficiency. If you don't have efficiency, then enough work gets done. If there's an error, you're not going to lose a spacecraft because it's not the same thing as the real-time system. If it's inefficient, it's useless. There's no point in having it. So it's very important to minimize waste of space and waste of cycles. That adds complexity, so that the background system may in fact be significantly more complex in many ways than the foreground real-time system. And because it's more complex, in order to be more efficient, it's important that it be portable, because your reliability may not come from absolutely comprehensive testing. Your reliability may come from reuse, from using in a wide variety of environments and a large variety of missions. So testing and experience is really where you get the reliability. Mutual exclusion. In real-time flight software, you don't mutex. If you lock things out, then you risk losing the spacecraft because you can't respond to an interrupt. Tasks will miss deadlines. But in the background system, that's not a problem. You have all these tasks that are running at the same priority level, and they can safely lock one another out because there are no task deadlines. As long as they don't lock one another out forever. If they run for a little while and have sole control, that's fine. And sole control of the CPU doesn't mean sole control. It means sole control at that level of priority. The real-time systems certainly interrupt them at any time. So it's unlike in the real-time flight software. It's fine to have loops and function calls inside critical sections, as long as they eventually terminate and let the other tasks run. And this enables you to minimize the cycles that you spend on task switching by letting software run for a little while it has a lock on shared memory. Which brings us to shared memory. Data sharing, shared memory, requires mutual exclusion. No good in the foreground system. You cannot afford to do this, and we don't do it. You don't use shared memory in the real-time system. In the background system, it's different. Because there are no task deadlines, mutual exclusion for a long period of time, which is a precondition to using shared memory, is perfectly okay. So shared access to data is okay, which is a good thing, because shared access to data in one place is the fastest way that multiple tasks can operate on the same data, and the fastest way they can interoperate and cooperate. So message passing, which is what you need to do in the foreground real-time system because you don't have shared memory, is perfectly, you need to do it in the foreground system. In the background system, in the real-time data management system, you don't need to do it because you have the ability to use shared memory. And it's good not to do it because message passing it takes more cycles. It involves, it's not as efficient as simply handing pointers around. The fastest way to interoperate is by sharing memory and giving semaphores when data is ready to work on. And memory management. Because the mission scope is fixed and known at the time you're going to launch, you can safely, in the real-time system, allocate arrays of objects that you know that are going to be sufficient to operate the mission. And so these fixed-length arrays with some margin are a very efficient and very deterministic way of operating on data in the foreground system. In the background system, your reliability depends on being multi-mission, and so you need the background system to be portable, you need it to be evolvable. So a good alternative, in fact, I would argue a better alternative, is to allocate a fixed amount of heap to the background system that is fixed. It's never going to change, but the management of that heap doesn't have to be simply allocating fixed arrays of objects. It can be a dynamic memory allocation system inside that fixed block. And that gives you a lot of flexibility in the design and operation of the non-real-time software tasks. You get efficient use of space, and it automatically adapts to changes in mission scope. So you don't have to rewrite the code when you move from one mission to another. And they can collaborate. The real-time system, the non-real-time system, there really is no conflict between the two. It's straightforward to use message queues to interoperate between the two, as long as the foreground end of the message queue is always non-blocking, and the background end is always blocking. And we have a practical example of this, and this was in 2008 when we uploaded the ION system onto the epoxy spacecraft and operated it as operated the spacecraft as a router in deep space, about 70 to 80 light seconds from Earth. The non-real-time system running in the background, dozens of background tasks, all running as idle, all running as the idle task, were all integrated with existing real-time flight software written by Ball Aerospace for DI, and without any modification to the real-time software at all. The interoperation between the real-time and non-real-time software was all through these message queues and shared memory objects on the background end. The software worked very well. Epoxy functioned for 4 weeks, passing 14.5 megabytes of data through essentially a delay-tolerant network. It was acting as a network router 10 million miles away. No data loss, no software failure over the 8 weeks of the experiment. So this is something that not only is theoretically interesting, it's practical. We've done it, and it's, I think, emerging as what we need to be able to do in flight missions as computers on spacecraft become more capable and the missions become more complex. And this is the other half of the same picture. And that's the end of my talk. Thank you.
Even if deadlines are long, they're still there. I mean, and after a while, if a task doesn't finish, that deadline becomes critical. For instance, like RAM scrub in the background, you just want to exercise and clear out your single bit errors via EDAC reads and writes. So why rely on cooperative multitasking when you're running an OS that could support, say, round robin for the background tasks?
If your operating system supports this natively, then you don't have to build it into the architecture. But not all do. I mean, if you're using an older or smaller spacecraft, an older and smaller processor, an operating system that's not equipped to do that, the architectural principles, I think, still apply. You can build this functionality into the hardware, into the operating system, or you can build it in the flight software.
Other questions? Very good. Thank you.
Thank you.
next speaker is Dr. Ray.